All right, so if you'd like to follow along with slides there, I have both a bit of a talk and demo, as many people have so far. So I'm going to go to a quick intro to the visualizer in case people want to actually try it out right now before I show it off, and you can just play around with it and see if it's intuitive in any way at all. And then go into some of the talk about AAM and abstract machines, which some people may know about and some people not. And finally, I'll go through a full demo for you guys. So first off here is what I'm going to show in just a second here. If you want to try going to analysesviz.gilray.net on your own, you can try this out. Otherwise, it's working. Excellent. What you're going to see is a visualizer like this. That needs to be bigger. There we go. And you can see, for example, I'm going to use this example in my talk. Wait, refresh that. OK, it comes in with this login at the beginning. This really isn't for security at all. It's just to separate one person's projects from another. So feel free to use guest. But if you want to create a project or delete one, please choose a different name there. And you're free to share the name with a friend, and they'll see your projects as well. So I'll go guest. And then you can click on one of these to see examples. This is kind of what it looks like. I just wanted to point out that you can click on some of these and some of these. And when you do, you have configuration environments, and you can click and get some more information by clicking down. So that's all I wanted to say about that. You can play around with that on your own if you'd like to. And I'll jump back to the talk here. All right. What are abstract machines? So that's the example I'm going to be using here. This is just quick let binding of two lambdas. One is U combinator, just x applied to itself, and the other is just the ID function. And we're going to see, and we see this just this little function that's ID applied to itself, which just reduces to the ID function. Applied to the U combinator just reduces the U combinator, and that's never actually applied. So with abstract machines, what we want is some kind of formal analysis of the reduction. So this is just a mathematical tuple that we put around our expression. We put some environment stack. They'll both be empty at the beginning. And this allows us to flexibly do this reduction syntax. So for example, the first step here would be to, what you do is you have you convert to a second tuple, which has all the next step in it. And then you just keep moving to another one at a time until you get down to a final result. So here, the next step from the first is just to take the first lambda, the first expression that you're trying to bind to the variable. And this is that first expression. It's the lambda. We have an empty environment. And our stack there just says that we're not going to do anything with the body now because we're going to do that. We're going to finish with that later. So that's finished at the moment. I put in italics both of those as just to represent some part of here. So the italics is not formal. And next we have to deal with the I. So the identity lambda has to be dealt with soon, but we're going to deal with this one at the moment. So that's kind of how this mathematical tuple works. And if I step a bit more, we have both eval, which is evaluating an expression, and we have apply, which is when you completely finished evaluating expressions, you need to actually do the computation. So eval works with the stack and choosing what to evaluate and getting values out of it. And apply takes the values. In this case, I may have closures in both I and I. And this step would be when I'm applying the I to I at the bottom here. So apply works by making bindings and moving on to the next eval. So in this case, the value for the I here would be this closure of lambda yy with empty environment. So we take the body of the lambda, be ready to evaluate that next. bind the parameters to the values, and don't do anything with the stack. So that was a single abstract machine in brief summary. We just step that until we get to a final result. But it's a lot of information in there, even if it is a formalized reduction semantics. The analysis of a program like this is just the list of states. That is the analysis. That tells you everything you need to know about how the reduction worked. But it is potentially infinite, which means that we may not be able to compute this. So we want to be able to solve that with an abstract machine. So we start out with these infinite, stack size is infinite, and also what wasn't shown would be if you have store allocation, the addresses would be infinite as well. But we do have some finite things. The program itself is finite, and any variable inside the program would be a finite number of variables. So the first step here we do is we take two problems and convert them to one by store allocating the stack. So now instead of an infinite stack, we just have more addresses. So all we have now that's infinite is the number of addresses. And finally, and this is the more abstract part, we use program expressions, variables, or some combination of those as our addresses. So for example, the location of a variable would be its address. The variable itself would be the address for the variable. And this means that the whole thing is finite, but there's some implications of doing this. Now that we don't have infinite addresses, multiple things may map to the same address. So for example, in our example, y may have mapped to both I and u. Y was when we were applying the identity function. I didn't have it on here, but the identity function was called on I and it was called on u. So the body of that, at some time, if we just use the y as an address, sometimes it's mapped to I and sometimes it's mapped to u. So now the store is mapping to a list instead of mapping to just one variable. And that means that when we step our machine state, that machine may step into one of multiple states. And we do still have soundness. What we call soundness here is that our list of machine states will include the full program run. In this case, it may have been the top one here, or it may have been the bottom. Or maybe as the program runs, one time it chooses the first and one time it chooses the second. But we have soundness in that the entire program is represented, but there may be spurious states that aren't a part of it. All right, so that was abstract machines. Unify the unboundedness, finitize the set addresses, and then find a way to get soundness out of this. And that means, so we get a systematic methodology for analysis, and we're able to work with tunability and tune that precision. I'll say that briefly in a moment. And we can get things like 0 CFA and 1 CFA, which are pretty common in multiple forms of program analysis. But we still have a lot of information, maybe even more information now that we had before, because we have states that may not exist in the actual program run, and there's not really an obvious summary of those. We've traded some precision for soundness and may get the spurious states. There is current research on how to tune imprecision. One of the most obvious ways to add instrumentation to these tuples. So if we're on the call site, I applied to I, we may just add that as instrumentation. This turns out to be a 1 CFA analysis where we're keeping track of the call site. So the call site is, and now if we have two similar closures that might be equal to each other, now the call site matters as well. So that adds some precision. So next I'm going to step into a little bit of what the visualizer looks like for the rest of the examples. This is, so 1 CFA, if we have put that instrumentation, this is just all the titles of the states, eval and apply, and a few more. We start this blue, and it's just a single path. And that does represent the full reduction of this program. But if we go to 0 CFA, it's going to be much more complicated. And so we get, at the beginning here, we're just creating and evaluating those lambdas, so that was just straight line, and the result just comes off. But we do have this spurious XX applied to itself, which just ends up in a loop of states. And that was because, as I showed you before at the store, at some point, y is going to map to both I and u. And if we use the y mapping to u on the first evaluation where I was applied, or the second when I was applied to u, now it's u applied to u, and so we're getting this spurious state. So, but we can see that in the visualization, and we're actually evaluating this function twice. So because there's no instrumentation here, and we're passing through this. This is the eval of the body of the identity function. And so we're passing through that twice. And you see that there's 2 arrows in and 2 arrows out. And so we'd like to at least simplify that a little bit. And so what we've created is this segmentation algorithm. We want to separate and evaluate only a function at a time in this in the visualization. So we're going to create individual CFGs for the functions, and then have a way to summarize the connections. When we complete that algorithm on this, what we get is a little bit less here, and this should be easier to understand. When we had the spurious x applied to x, there's just a single node that says we're never going to return. We've replaced all of that with a dotted arrow here. So because that apply calls a function, and then a function we're going to have that shown elsewhere. We'll have multiple functions showed. This is one of those functions. And the dotted line just hides the next one. So we're not going to deal with that function in this view. And then here also you see the 2 arrows in and 2 out, and we're calling the function. In this case, there was only a single node when that function was run, so it didn't help much. But you can imagine if this was a far more complex function, that bringing it down to a single node would help visualize what's going on here a lot better. So how that segmentation algorithm works, I'm going to jump back to the simpler view here to talk about that. This is fairly simple. What we do is we take one pass over the entire CFG and find all the call sites. These are the apply states. And find the entry points. Now we know all of the functions that are going to be called in the run of the program. And we pick the function you want to work with. So in the case of our visualizer, we're picking the syntactic lambda. So all calls to that particular lambda. This one is the ID function. We put them all into a single state. So this super state really represents all the calls to lambda YY. And then we just step the state. The markers represent the individual function calls. We just step each one of those preceding state, machine state, and to make another super node. In this case, they both are returned, so we're just going to put exit on here. So and then this is the final result this is the final visualization of that function, of the ID function. Is just evaluate the body once and you're done. And then for in order to skip over functions to make those dotted lines, we do something similar. We walk the entire CFG and find all the return points, their exit points. And this really is keeping track of the stack address, so that when we do reach an apply state when we're producing the function, we make a call. We can just read off the address that it's going to be calling out to, and look up the exit. And in this case, it's just one point, but there could be multiple exits as well. And then we can skip over anything that was in between. And that way we can make those dotted lines and make individual functions. So that brings me to the demo. Again, it's available online if you want to follow along with me, and the code is available online as well. Oops, mirror. So we saw this example for this. What I really can do is make a whole new project. So I'm going to make a new project. I've got this ready. I can paste some code to an analyze and hit process. And there we go. So we can do the analysis live. And what we've got is these states. So this was much more of a jumble than I hoped. But maybe now you can see what we had before. This was that XX applied to itself circle. This was the loop of calling multiple functions, and then this was the initial. And as you see, as I'm hovering over there's a lot of functions for navigation and for viewing. So we've got the code up here. I can hover on parts of the code, and you can see certain nodes in both the top and bottom section there are highlighting as I go. I can also click on one, so if I click on I here, it's going to highlight this node, and we get the configuration. So that says the syntax we're doing is I. We're evaluating. I is representing this function here. This had no instrumentation because I just did a 0 CFA. And the stack right now we're waiting on 2 applies. And it has an environment number 2, which is already shown, which right now says the I is mapped to one function and U is mapped to the other function. And then I can even click on the environment that's inside these as well. And that, in this case, is the empty function, empty environment. And I can remove it if I don't like it there. And then we can also click on one of the, I clicked, but in this case there's 2. One for evaluating that application, and one for actually doing the apply of that application. Step in. And each of the states may be a little different. Let's see what we got. No, they're both the same in this case, but one doesn't have an environment because it's just the apply state. May not have an environment. And what we've got up here, which was not in the talk, is the summary of how the functions relate to each other. So this right now, with nothing highlighted in the top, is the full nodes of the main AAM analysis. But if I click on main, which is just the whole expression, as if there was a lambda around it, you see what we had shown before, which is we have these dotted lines. And I can even click on the dotted line, and it's going to highlight where that's pointing to. And so what this does is that main function, it has dotted lines that call out to I, and another one to I, and another one to U. And so you see that. You see a line to I here and a line to U. And then I just has its exit dotted line. So we put a dotted line up here to exit. So this is a call and a return. And U here is just called on itself in this analysis. So it has one dotted line to itself. So we have the line to itself here. And then we can, for example, fork a project and go to a 1 CFA, process that. And you see what we had before. This is a single line of states. And the main, in this case, is also a single line. But you notice now in the main function, we have these 2 dotted lines, and they're separate, because this is this fully instrumented functions, so the calls are at different points. They don't point back to the same node. And one way to check how this may work is that if I go into main and I check the apply state, one entry under there, return state, one entry. But if I went back to the previous one, this eval has 2 stacks. So we can see that this is one evaluation that has 2 possible return points. But in the 0 CFA, this apply, or the return from it, in this case, instead of having 2 stacks, it has actually 2 nodes inside of it. One which will return in one case and one that's returned in the other case. Instead of having two different return points, it just has 2 different complete machine states. Yes, that's that. That's available to use and play with now if you'd like. We have pretty simple syntax right now. This, as you saw, we also have conditional if. And you can do multiple parameters in the lambdas. I think that's all I wanted to show. Back to the demo. So some future improvements we're looking at is more highlighting of different expressions or different parts of the visualizer as you look over things. Maybe highlight environments that may be contained inside states, depending on where the mouse is. Things like that can help you know where you're at. We want to completely overview the stack visualizer. What you saw was just some text I printed out. We don't have anything there yet. Additional language features, maybe some more navigation options, and any suggestions other people might have for how to work with these AM analyses, how to explore them, and what you might need. And that's it. Well, so what I went over is how to analyze a program with an abstract machine. That these things may be pretty complex with an imprecise graph. But what we did is we separated out into functions to simplify that a little bit and have a visualizer for you to look at. So, thank you.
All right, we've got plenty of time for questions.
You can go first. Have you thought about visualizing pushdown analyses? Because some of the collecting things together reminds me of faint memories of people trying to explain pushdown analyses to me, and it never quite clicked. And I wonder if your visualization can say, here's where stuff is happening. I don't know. Have you thought about pushdown analyses?
We haven't. We have just worked with this. One thing I forgot to show was we have an import and export. So that it produces a JSON string of our data in or out. And so you can, if you know what you're doing, you can kind of create your own string and use the visualizer to visualize that. But we haven't actually tried to work with anything but this at the moment. Yeah.
So I was curious how large of programs have you tried this with, and how well sort of does this visualization scale to, analyzing sort of a larger program? I know that your language is still kind of restricted right now, but I was just curious how big a thing you tried to throw at it.
So we haven't actually tried throwing at it something really huge ourselves. We've seen multiple tens of nodes.
Okay.
We haven't tried ourselves hundreds of nodes. We probably should just throw it at it and see what happens. On a slower laptop than when we were creating this, we realized there was already some slowdown, but that was from just not being efficient with the web interface and with Node and React that someone was working with us for. So right now the highlighting, if you have a slow computer, just doesn't it doesn't quite work the way we wanted it to. It works pretty well, but you can tell there's slowdown, and the highlighting really shouldn't slow it down. So our next iteration will probably be to working on performance.
So just to be clear, when I say scale, I don't just mean the performance, but I actually also mean like, so I have part of the idea here, right, is I'm separating the complexity of the full graph and the complexity of looking at a single function.
Okay.
It's not uncommon for me to have pretty big functions as well, and maybe I may want multiple levels of that abstraction capability, so that if I have a big function, I still can look at some part of that function or some subset of that function to figure out information about that, rather than having sort of this just the single level split. And I was curious if you'd run into anything
okay.
that would cause you to maybe want to have a multiple levels of the sort of call.
Okay, so good question. We haven't, because we haven't tried it on very large analyses, we don't really know where the boundary of where we're splitting it is. We chose the function boundaries because that was just fairly obvious to start with. You're suggesting maybe to include some functions in there and not skip over them, and also to divide the function itself and just say, stop here, and then we'll see the other half of the function in another window or something.
Yeah, something like that.
Yeah, we haven't thought about that. That's definitely something we could consider, and it shouldn't be too hard. But the user would have to say, here's the point.
Have some way to specify
And so we have to originally have something there and then just separate it. But yeah, that could be a thing. Yeah. Thanks.
Cool.
Anybody else?
I've got a question.
Okay.
So do you have the ability to, or would you be able to add the ability to do diffing? I don't know if anyone asked that one already. So you could have maybe either two different programs or two different analyses of the same program and want to be able to look at the diffs.
Yeah, that would be, that sounds like a good thing we could use. Right now we had, so as you saw, I showed 1 CFA and 0 CFA. You couldn't see the diffs, but you could switch between them and kind of, yeah, it's not very good, I guess, if you just want to do that. But if you can find the node that you're looking at, as I showed in the demo, then you can see the difference. But yeah, that would be good. But problem with that is we'd have to match graphs, and that is a very tough problem. So someone else needs to do that research and plug into our analysis so we can get them together. I know people are trying, but it's one of those really tough problems to lay out graphs over themselves and say this is the same and this is different. Yeah.
Any other questions? All right. Thank you, Kyle.